Okay, so first of all, hello to everyone. I have to say at first that unfortunately the main presenter and the main author of this talk unfortunately got ill. So I will replace my colleague Timofey, and that's why maybe I will not be able to answer all the questions about the technical details of the analysis I'm going to present, but I will try to do my best, and I will be able to address you to all these questions to Timofey as soon he's getting better. The name of the present talk is Task Classification from Pre-Stimulus Functional Connectivity on EEG data. And basically the background of the present talk is the importance of pre-stimulus functional connectivity and functional connectivity reconfiguration for task performance. First of all, it has been shown that functional connectivity characteristics are unique for different cognitive tasks. Next, it has been shown that actually functional connectivity reconfiguration before the task can be used to predict the quality of the performance. In the paper by Ekman in 2012, it has been shown that from functional fMRI-data, it was possible to predict errors from pre-stimulus reconfiguration patterns. So in the present study, we were interested in whether we can actually predict different types of tasks from functional connectivity characteristics and its possible reconfiguration. What is our design? So our subjects were presented with three types of stimuli. It was either algebraic equations with and without error. I will show you how it looked. It was arithmetic equations with and without errors, and it were sentences in native language with and without errors. The participants' task was to indicate whether they could find an error in the present equation or a native language sentence. So 76 participants took part in our experiment. The age was from 17 to 34, with average about 21, 22 years old, and 30% of the sample were female. The experiment looked like this. So first of all, there were not only tasks, but before each task, every participant was presented with the cue indicating what would be the future task. So they knew that after 2-second wait, they would be answering the question either about arithmetics or about algebraic equations or about native sentences. For their task performance, there were unlimited time, but it was really quickly and took less than a second or two to perform the task. And the participants were shown feedback whether they succeeded in all these tasks. I have to say that the equations and the arithmetic equations and algebraic equations, as well as the native language sentences, were all pretty easy. So the average accuracy for every types of tasks were higher than 80%. So basically, all the subjects did really good in performing the tasks. And we were interested whether we could predict what task, whether we could predict the task from the 2-second wait period before the task. So our idea was that after the cue, the participant had to expect the specific task, and the neural system should start with reconfiguring itself to be better prepared for the specific task. And we used this 2-second period to predict what type of task will be shown later. So what did we do? We recorded 44 channel EEG and used 0.1 to 30 hertz data with 150 hertz sampling frequency. All the data was automatically pre-processed with auto-reject package for M&E Python. For each trial, we used 2-second pre-stimulus interval to estimate functional connectivity, and we used imaginary part of the coherency to estimate the connectivity between different EEG sensors. All the data was analyzed in 5 frequency bands separately. It was alpha, beta 1, beta 2, theta, and we used full range data for 4 hertz to 30 hertz, and we left all the data below 40 hertz because of the several papers showing that functional connectivity EEG data are unstable in lower frequencies, so only higher frequencies were used. For each functional connectivity metrics, we used a threshold. We took only 25% of strongest connections to build a graph, weighted graph in our case. And for each graph, for each participant, we calculated 5 global measures. It was median path length, it was assortativity degree, it was average clustering of the graph, global efficiency of the graph, and average local efficiency of the graph, as well as 5 types of local measures for each EEG sensor. It was rich club coefficient, the degree of the node, clustering coefficient of the node, between the centrality of the node, and key core index of the node. So altogether, for each participant, we had more than 300 entities in total, which was used as a network fingerprint of the exact participant. We used the M&E Python package for EEG processing, as I said before, and for the classification, we used scikit-learn package for Python, and we used multiclass sparse logistic regression as a classifier with leave one out as the train test split to check the accuracy of the classification. Unfortunately, I have to say that we were not really successful in correct classification. Only from 31 to 38% for different types of tasks were classified correctly, which is below or just a little bit higher than the chance level for classification. So actually, there were no predictive data in functional connectivity in pre-stimulus time for the in our experiment. At the same time, we were interested whether it was just our algorithm that maybe was broken in some sense, and maybe it's just the problem of the classification approach. We checked that with another type of task. We were interested whether we could try to classify the participants and from the network fingerprints we obtained. And for these tasks, we showed that actually the algorithm was working, and from 61 to 90% of the accuracy was we showed that the accuracy of the algorithm to predict different individuals was up to 90% for different frequency bands. Here we think that these results show us that actually all the functional connectivity EEG data can be highly variable across individuals, and maybe the problem with our initial task classification was because we didn't properly address the problem of individual differences in the sample. So basically, the algorithm worked for individual differences, but didn't work for classification of the future tasks. And we had some limitations in our study. First of all, the topological our initial idea was taken from the fMRI study, which with much higher resolution, spatial resolution of the data, and maybe the 64-channel EEG might be just not good enough for this kind of tasks. Maybe the topological resolution is not adequate for the types of task we were interested in. Second, unfortunately, the graph construction is routines are highly variable across different types of studies, and we used only one synchronization measure for graph construction. It was imaging parts of the coherence, and we used only one type of the threshold to calculate the weighted graph, 25% threshold. Maybe different types of synchronization measures or different types of threshold could lead us to different results. We want to look for that into our future analysis. And our last thing is maybe the averaging across the whole 2-second period could lead us to losing the temporal dynamics of network reconfiguration, and actually it's not so sensitive to the just this 2-second period, but maybe millisecond temporal changes in the network reconfiguration are much more important for the classification of the future tasks. So basically, these three issues we want to address in our future analysis. And basically, that's all. We tried the working method, but didn't succeed in good classification. And we want to go further, looking into further details of possible analysis routines. So basically, it's it. That's it.
Great, thank you. So, is there any questions from the audience? Please feel free to ask. So let's see whether somebody wanted to say something. But yeah, I actually wanted to ask you, you mentioned something like individual differences might matter. So does it mean that, for example, there were much variance in the, I don't know, grammatic, or I mean grammar, I think is Russian, right? Or you know, math level, math knowledge, or something like that? Or what do you refer to?
Well, actually, we think that there are a lot of things that can matter. Actually, this is a part of a bigger study that was related to studying math anxiety and its impact on the neural response to different types of tasks. And we know that there are a lot of individual differences in the sample regarding IQ level, regarding their math anxiety quotations, like so there are a lot of differences. And in our initial analysis, our first try we will go on, we averaged it was averaged for the whole sample, and we were looking for the classification without addressing the individual differences. Maybe if we will try to do that on the individual differences level of analysis, adjusting for some other variables, or just doing it within subject analysis, maybe it could lead us to better results.
Right, or just separate into groups the low and high performance.
Or separating or regressing out some other variables. So basically, we know that there are a lot of individual differences, and actually there are some studies that network fingerprints can be used to correctly identify the individual with more than 99% of accuracy. In our study, it was the highest level was 90% accuracy, but altogether network fingerprints are highly unique, not only for different types of cognitive tasks, but also for different individuals.
Yeah, great. So yeah, another quick question. How do you compare between tasks? I mean, because how I see it that probably the algebraic equation is slightly more complicated or more complex than the arithmetic, or maybe for some people it's easier the sentence, or have you ever
Yeah,
compared that?
of course, there are different difficulty level. However,
Mhm.
this our accuracy was from in this 30%
Oh,
zone
I see.
for all types of tasks. So it didn't really differ for different types of tasks.
Oh, okay, I see. That's great. And is there any reason you just only 30% of the sample were women, or it's more like
It
a?
was just
I see.
yeah, we know that there's an issue, like there was no particular reason for that, and we want to actually invite more women to the experiment, but at the time we just had that sample.
Yeah, have you compared? I mean, I know it's not fair because it's 30 and uh, 70%, so it's not really a fair comparison, but just like a test, have you compare between women and men and see whether there is any
No,
difference?
no,
Not
not
really.
yet. We were more interested in individual differences in general, like, and we want to address that regarding the gender. And maybe like I don't think that our sample is enough to really look into
Yeah,
gender differences at all. We need a bigger sample for that.
that's right. Okay, let's see whether somebody else wanted to ask something. I think it's not the case. So I just wanna thank you so much. Yeah, it was a wonderful talk. I think it's a really interesting study. So yeah, good luck with that, and just let us know when you publish your data. Okay.
Okay, thank you. Thank you very much for your questions.
Okay. So thank you, everybody, and yeah, see you.